sklearncovariance. Description. The covariance matrix in scikit-learn sklearn is a fundamental tool for understanding the relationships between variables in a dataset. It quantifies how much two variables change together, providing insights into their interdependence. Covariance is particularly useful in various data analysis tasks, including feature engineering, identifying correlated features that might be redundant or contribute similar information to a model. Dimensionality reduction techniques like principal component analysis (PCA) rely on covariance to identify directions of highest variance in the data, enabling data compression without losing significant information. Machine learning covariance plays a crucial role in algorithms like Gaussian naive Bayes, where it helps model the relationships between features and target variables. Inputs: X, a NumPy array or pandas data frame representing the dataset. Each row corresponds to a data point, and each column represents a feature. Outputs: Cov, a NumPy array representing the covariance matrix. The element at I, j represents the covariance between the ith and jth features. Steps: 1. Data preparation. Ensure the data is in a suitable format, e.g. NumPy array or pandas data frame with features organized in columns. 2. Covariance calculation. Scikit-learn's covariance function computes the covariance matrix. This involves calculating the average of the product of deviations from the mean for each pair of features. Metrics: covariance value. The magnitude and sign of the covariance value indicate the strength and direction of the relationship between two features. Positive covariance: the features tend to increase or decrease together. Negative covariance: the features tend to move in opposite directions. Zero covariance: the features are independent or have no linear relationship. Visualization plots. Heat map: a heat map visually represents the covariance matrix, with colors representing the strength of the covariance. Darker colors indicate higher absolute values, while lighter colors indicate lower values. Fine-tune parameters. Rover: a Boolean parameter indicating whether each row of X represents a variable rover true or an observation rover false. Default is true. Uncertainty methods. Confidence intervals. Estimating confidence intervals for the covariance values can help quantify the uncertainty associated with the calculated relationships. Challenges and fixes. Challenge 1: data scaling. If features have vastly different scales, the covariance matrix can be dominated by features with larger variances, making it difficult to interpret the relationships between features. Sample use case that resulted in challenge 1: consider a dataset with features representing income in thousands of dollars and age in years. The income feature would have a much larger variance than the age feature. Fixes to challenge 1. Standardization. Transform the data by subtracting the mean and dividing by the standard deviation. This ensures all features have a mean of 0 and a standard deviation of 1, allowing for a more accurate comparison of covariance. Challenge 2. Outliers. Extreme values. Outliers can significantly impact the covariance calculation, leading to misleading results. Sample use case that resulted in challenge 2. Imagine a dataset with the heights of people. If there's a single outlier with a height much taller than the rest, it will inflate the covariance between height and other features. Fixes to challenge 2. Robust covariance estimators. Employ robust covariance estimators like the minimum covariance determinant (MCD) method to minimize the influence of outliers. These methods identify a subset of data points that are less likely to be outliers and use only this subset for covariance calculation. Data preprocessing. Remove or handle outliers using appropriate techniques before computing the Covariance. This could involve replacing outliers with the mean or median, or using outlier removal methods.